So I suppose how many of you are in the other course that I'm teaching on programming for data analysis? Okay. All right. So my name is Kasturi Kannan, and I'm also part of this course. If I have put up some reading materials and things for you in this website, so if you go here, you'll see some of the additional topics that you can learn, as well as everything. This lecture, the link to the lecture is here, as well as I have it in the presentation format. So if you want to go back and revise something, you can do that. Okay. So let's get it started. How many of you have a formal training in computer science? You? All right. So it's good because I have kept this lecture to a very basic minimum. Okay. So it's designed to give a bird's eye view of analysis of algorithms. Okay. Who has done some mathematics courses in here? You all have some basic math courses. Okay. The subject is really vast. Okay, so it's a full semester course in most of the computer science departments, and I'm trying to making it in this one lecture. So all I can do is like give you a very basic view of what analysis of algorithms is about. Anybody of you have thought about this subject or read about this subject a little bit? Have an idea of what it is? Okay, all right. So motivation. Computer programs or set of instructions, right? So this was the basic algorithms have been thought through even before the advent of modern computers in 1930s. People have thought through these logic. Turing was one of the influential person to do some basic developing some rigorous logic for algorithms. And there can be several algorithms that can accomplish the same computational task, right? For instance, sorting a bunch of cards. This could be done at least in two different ways. One is a standard insertion sort, like what you do, we have a bunch of cards, you take one and look where you have to insert the card. And so that's a basic insertion sort. And there is also what is known as a selection sort. What you can do is you can place the pile of cards and take the minimum, keep it in another pile, and take the minimum from the rest of the cards. And so you can do a select minimum every time, right? That's another way of doing it. So you can do the same sort in two different ways, right? Which is a better sort in terms of time. Like if I give you 1 million cards, for instance, right? Which is a better sort when you have these two types of ways that you can sort cards. Right? So the better is often referred to as computational complexity in the context of analysis of algorithms. All right. So the fundamental to this analysis of algorithms is a complexity analysis. Okay, so which determines how we can evaluate such sorting for instance, in sorting procedures, how can you evaluate the time that's needed if you as a function of input size, right? It does not depend on the programming language. A programming language could be Python, it could be R, it could be C++, anything that you want. But regardless of the underlying programming language or even the architecture, for instance, we want to evaluate and compare algorithms, right? A programmable idea, an actionable idea, a pseudocode, right? Not really a code, and how things could be computed. So we are not interested in how fast a program actually runs. That could depend on several factors, including how the language is structured. There is a whole theory of programming languages. So we are not interested in how fast it's actually running, but how best is the design of the program, regardless of how it is implemented, right? I mean, for instance, a person could run sort it faster or slower, right? But we are not interested in that. But what we are interested is the fundamental way that one sorts is whether how efficient or inefficient it is, right? Such a meta-analysis enables to say that one algorithm is better than the other algorithm. So that's the basic idea of analysis of algorithm. Also, the complexity analysis would help us determine, depending on the input size, how things can, if it becomes large, we will be able to have a prediction. So that gives you a power of predictability, right? Mathematics is one of the strong languages to do that. And so So for instance, also you can give some numbers that are sorted or random numbers. How does the algorithm behaves, right? I mean, most of the real world data does not really or not really random per se. They will have some correlation. So analysis of algorithms will be able to tease out when the input is correlated, when they have when there is a correlation among the inputs, how things are behaving, right? And such predictions are important for practical programming, right? I mean, to determine the worst case, best case scenario, it's very, very important. So analysis of algorithms gives you a tool to do that. How do you count instructions? So analysis of algorithms begins by counting instructions, okay? So let's say that we have to determine the minimum element in this array A with n elements, right? So we have an n element array. So this code, this pseudo code actually performs the minimum. So what it does is that it first assigns the first element to a value am, right? And then it goes over the array for I equals 2 to n, you increment the index, right? If a of I is less than or equal to m, you replace m with a of I. So this is the simplest form of finding the minimum in the array, right? You have an array, you first take each element of it and then compare it with that element, and if it is not, you replace it. I mean, this is a straightforward way how we find the minimum, right? And then you print m is the smallest and return m, right? So to work out the complexity, we will assume that there is a hypothetical machine that can perform these things. Let's say that it can assign a value to a variable. It takes just one instruction to assign a value to a variable. So for instance, here m equals a of 1, right? It's just assigning. So that takes one instruction. And looking up the value of a particular element in an array, that also takes one instruction. And comparing two values, that takes one instruction. And incrementing a value, as well as basic arithmetic operations such as addition or multiplication. We don't want to get into the details of how the machine performs it and depending on the architecture or the programming language. Okay, let's assume these cases. Okay, so the first assignment statement, right, m equals a of 1 will require how many instructions? 2, right? Because one for looking up a1 and the other for assigning a1 to m, right? So it takes 2. So the first time of the for loop, right, I has to be assigned 2 and the condition here for the first increment, right, for I equals 2, right, it has to, so you have to assign, right, as well as increment. So that takes 2 more instructions, right? So, and also this has to be done for I equals n, right? It has to go through the entire array. So the total number of instructions that would just cost for this is 2 times n minus 1. Okay, no questions so far, right? So we can define a mathematical function g of n that takes n and then it spits out, ignoring the body of the for loop, what is the cost involved in here. So it's two instructions for the assignment. For the initial for loop assignment, it's 2, and then 2 times n minus 1. So it's 2n plus 2n plus 2. That's the mathematical cost for going through the for loop, right? Now we have not yet discussed what happens inside the for loop, right? So for when you go inside the for loop, you have this statement: if a of I is less than or equal to m, you swap it. Okay, so this actually depends on the values, right? This requires 2 instructions, one for a of I and for comparing a of I is less than or equal to m, right? This requires 2 instructions, but this is also depending on the values actually of the array, which we don't know, right? So what we can do is we can take the worst case. What happens? Let's say that an array A is 4, 3, 2, 1. Okay, so in this case, the if loop will be executed every time because the first element will be 4 and then it will look up 3. Oh, 3 is less than 4 and you have to swap it. Again, it's going to take 2 and it's going to compare with 3 and it has to swap it, right? So it has to do every time, right? So whereas, for instance, if your array is something like this, it will not be executed at all. It's just once, right? Because the first element is there, the if loop will not be executed at all. So depending on how your elements are, the if loop changes, but you can compare it with the worst case as well as the best case. Okay, so often we'll be interested in the worst case behavior. right? So once you determine the worst case, that's the maximum that we would be spending, right? We are highly unlucky. And in this case, so if the if loop will be executed every time. So there will be two times for every iteration of the if loop, and so this cost is going to be 4 times n minus 1 for the entire for loop. Okay. So the worst case complexity in total is given by the 4 for the initial if for loop and then 2 times 2n minus 1 plus 4 times n minus 1. So the total cost is going to be 6n minus 2. Okay, so this is the worst case complexity. And also for the best case complexity, the if will not be executed even once. So the entire 4 times n minus 1 term will not be there. So it's only 2 times n minus 1. And so giving us 4n. Okay, so this is what it means by the upper bound and lower bound, the worst case and the best case. It gives us a heuristics on the number of instructions in the extreme cases of the input. Okay, so that gives you an idea of how bad your algorithm could be structured or how best your algorithm could be structured, right? So we should also keep in mind that the actual CPU, it also depend on the compiler in our program, right? For instance, we have to think that in this assignment, it just takes one assignment in C, right? But it would take in Pascal, it's executed like this. It takes so many instructions. So we are not really interested in all these nuances of how things are executed, right? So it makes total sense to ignore additive and multiplicative constants in our analysis, right? And keep only the rapidly growing term. So this is such an analysis is called an asymptotic analysis. So for instance here, the worst case is 6n minus 2, right? The leading term is n, so it's just n. So mathematically speaking, it would say that W of n could be as bad as n. Okay, the worst case could be as bad as the number of inputs. So if you give a million input, it's going to take hypothetically million units of time to execute it. Okay, so that's what we mean by the asymptotic analysis. Okay, so we are not interested in all these multiplicative constants and blah blah. We are interested in a more broader picture of how efficient the algorithm could be based on the input size. So for instance, let's analyze the same kind of a task that we did before, but then we have to print the smallest number in a matrix instead of an array. So what is a matrix? What's a matrix? 2D array, yeah. So okay, for now it's a 2D array. Day after tomorrow it's going to be a different thing. Okay, it's a 2D array. So you can find this 2D array. If you want to find the smallest element through a brute force approach. So what in general in computer science brute force approach means that we test all possible outcomes. It's a worst possible. Well, in the sense of designing, it's a natural way of doing things without too much of mathematical insight in developing the algorithm. It's called a brute force approach. Okay, so you check for all possible candidates. You're not looking for optimal way of doing things, but you're trying to look for an exhaustive search, right? So for that, for a matrix is just a 2D array, right? So what you do is this: assign m to the first element of the array, and for every row we iterate through the columns, right? It's a simple way of doing things. So you have a two for loops. So if one is incrementing I and the other is incrementing j, and if aij is less than or equal to m, then you replace m with a of ij, right? It's and the smallest, you note the smallest element also, right? So in this case, right, if we assume all the above criteria for a hypothetical machine, like it costs one computational one instruction for assigning, etc., etc. So this line 2 is going to take 2 instructions again by the same logic, right? And in the worst case, the matrix A could end up like this. So the for loop would be executed every time, right? And the if could be executed every time. So we have n squared, right, costing 5 instruction. So therefore the worst case complexity, you can work it out, it's 4 plus 5n squared plus n, right? So in this case, the asymptotic behavior is we ignore the constants, and we take the rapidly growing term, right, which is order of n squared. So that's what we say, it's as bad as n squared. Okay. So for instance, in one of the algorithms that you design, you get like 3n plus 2. The asymptotic behavior is given by order of n. And for instance, you have a constant, right? You say it's an order of 1. And what happens here if you have n plus square root of n? Which grows faster, n or square root of n? N, right? So it's order n. And what about n plus exponential of n? Exponential is going faster, right? So this is some exercises that you can work out. What about this? N power n plus n. Obviously n power n. So that's the idea behind analysis of algorithms, that you design, you see what's a rapidly growing term after you work out all the costs for instructions within a for loop, or if it could be a while loop or anything like that. So the complexity of selection sort is what? You take the minimum every time, right? So you maintain a 2 subarray, one array which is already sorted, and the remaining subarray is unsorted. So every iteration you pick the minimum and then you insert it into the unsorted array, right? So that's from the unsorted array move to the sorted array, right? So for instance, here you have an array 64, 25, etc., etc., right? You find the minimum element in this array and place it at the beginning, right? 11, and then you go here and then you look, find the minimum of this array and then place it at the beginning. So it's like 12 now, and then you go again to the rest of the unsorted here, and then you will see that it's 20, 25, 24, and then later comes 64, right? This is a simple selection sort. And what's the pseudocode for it? For every time, right? What you do is for I equals 1 to n, you increment, and then you find the minimum in the array, right? Where the minimum is, we initially discussed the minimum function, right? You swap, print and return in the array, right? So what's the complexity of this? How does this work? What happens inside the for loop? You have two arrays, right? One is a sorted list and the other is an unsorted list. And every time you take one from the unsorted list, minimum from the unsorted list, and put it in the sorted list, right? So the number of elements gets reduced every time in the unsorted list, right? By 1. So initially, although we don't know the actual complexity, right, because of the numbers in there, at the first stage you will have n elements, and the next time you will have n minus 1 elements, right, for the going through the array, right? And so this is adds up to n times n plus 1 by 2, which is order of n squared. So the complexity of selection sort, the worst case complexity of selection sort is order of n squared. All right, so that gives you hopefully some basic ideas on algorithms and how they operate, right? Who have how are these algorithms implemented? What do you need to do these algorithms? Data, right? You need to store the data, and you should be able to access the data in some time, right? So these are one of the fundamental things that we do in computer science is basically organizing the data, and data structures are one of the most important subjects in in computer science. I mean, it's like it depends on whether you store the data as an array, or you store it as a list, or you store it as some other data structure, right? Whatever that you're doing, the data is stored in some form. What's the form of the data, right? So mathematically or logically, the models for such organization is called abstract data types. Okay, an example of an abstract data types will be a list. Okay, so the list, we should be able to store given number of elements for any data type, right? Need to modify the elements by position, should be able to access the elements, and also modify element at a read the elements by position, and also modify the element at a position, right? So these are some of the preliminary things that you may have to do on data, right? So we need also a concrete implementation of an abstract data types, right? For instance, arrays, right? Arrays are different from lists, right? So, and also there are some basic atomic types like numbers, strings, and booleans, right? And there are also some composite data types that are made of several numbers, for instance, arrays, records, and lists. that are made of these atomic data types, and they are called composite types. Okay, the simplest data type would be a node. It just has a value and also a reference to where that value that node points to. Okay, so that's an implementation of several other data structures. So for instance, here in Python, you have a node, and the node is defined like this. You have an item, and then it points to the other node. Okay, these are the two basic things a node has. And from there, we should be able to get an item from the node, what's the value in there, or it has to go to the other node, right? And we should be able to set the value of the node, and we should be able to set where the node points to. So these are the four fundamental operations that you do on a node. Okay, so this is a Python implementation of it. And also you have a linear data structures like arrays. Arrays are a fixed sequence of elements. They are stored logically and contiguously, right? It's a container that holds a fixed amount of items at any time, right? I mean, so most of the algorithms, most of the data structures, right? I mean, they make use of array, right? Array is a simple implementation. So if you say go fetch the value of 5, it's going to go. You have a specific a section in the memory that's 5, and it's going to fetch that, right? The computational complexity for reading and accessing an array is just 1, because you already know where to go. You know the number, so go and fetch it, right? I mean, so no matter what the number of elements in the array, the calculation to find an element is just a single multiplication and addition. Exactly, if you tell the number 5, there is a specific location in the memory, it's going to go and fetch that number from there. So it's a specific, so the complexity of inserting an element in the array, right, is order n, right? Because you have to find the end where, if you have to insert it at some position, you have to compute where it's going to go and then insert it, right? So so the inserting in the middle of an array, right, it's going to be difficult. Whereas you can insert it in the last or in the first, it's pretty easy, right? So because it has to be shifted one index up, right? Whatever the index is there, it has to shift one index up. So it's going to be order n, right? But whereas the linked list is a structure like this, it has a value, it has a reference, right? That's all it has. You can make a node like out of the blue, and you can put that node into the linked list. So it's different from an array. An array is a set of locations in the memory. We already know the address of the memory, right? So you can go and point there and get the values. Whereas for a linked list, it does not have a structure like an array. It's not sequentially organized. It could be anywhere. All it has is a value, and where you want to go and fetch the other, it points to the other, the next node, so called the next node. It's not a sequential node. Okay, so that's the linked list. Okay, so there is a big advantage of linked structure, right? We will be easily able to remove and add and remove elements. If you want to add an element, it's pretty easy. Just make a node. That's it. I mean, you know, it's pretty easy, right? To insert an element is just create a node, add value to it. You have a reference, right? So you make up a node, and you have a reference, and then you point that node to this node. So you should be done, right? But whereas for array, it's difficult, right? They are sequentially stored. So each node is created separately and given a spot in memory, right? So this is just one spot in memory. It doesn't matter where it is. And as long as we are able to keep where the head is, we will be able to track the entire list. So it has the pointer to the next link. So you can access, and you can go and access the next node. Okay, it need not be sequentially arranged. It could be arranged in any way. Okay, so linked lists are preferable over arrays when you need a constant time insertions or deletions, right? I mean, it's just like a flash. You can create a node, so you don't know how many items will be in the list. Most of the time, you really don't know what's the incoming size. In that case, it will be very, very useful, because you can just create and delete it. You don't need random access to any elements, right? And you want to be able to insert in the middle of the list. Okay, so as a priority queue. Arrays are preferable when you need an indexed random access to elements. If you already know that, okay, this is the volume that I'm going to get not more than 5 values. you can sequentially order them, right? And you know the number of elements in the array, so you can predict the amount of memory, right, for the array. And when you need speed, right, for the linked list, you need to go trace to one node to the other. Whereas for array, you don't have to do that, right? And memory is a concern. If there is a concern in the memory, then the arrays fill up less memory than linked list, right? I mean, because each element is just one data, right? So you don't have a pointer also. So list gives us benefits over arrays, but can dynamically allocate resources. So I mean, so performance-wise, lists are a little bit slower than arrays, but in general, lists are preferable nowadays. Memory is not a concern, storage is not a concern. So in general, lists are preferred, right? There are special types of linked list. One is called as a queue, right? A queue is a linked list. It's just a linked list where last in, if you it's first in, it's last in last out, or first in first out. That's a queue. Whereas for a stack, last in first out. So you will be able to insert only through, if you insert an element, you have to pop it out before you insert another element. That's a stack. So for instance, stack exchange, you know about stack exchange and stack overflow, right? Can ask questions in there. That's a stack implementation of it, right? I mean, because it's a last in first out. I mean, if you're asking a question, it's better that you get an answer immediately, right, rather than wait for the first person to have answered, and then the next person to have answered, and then coming to you, right? So that's a nice way of implementing. If you ask an answer, if you get an answer, you'll feel good about it, and so that's the idea behind stack exchange and stack overflow. And these are linear data structures. Although lists are not sequentially arranged, they are linear because you are able to access one element after the other element, right? There are non-linear data structures as well. They are trees and graphs. Okay, so you can order things non-linearly. So trees are not linear structures, and more than one possible direction is possible. So from this node, you can go to this node, or you can go to this node, right? I mean, there are multiple ways that you can go in a tree, right? And tree traversals are not that straightforward. So the process of visiting each node in the tree exactly once in some order, right? I mean, there are several ways that you can visit a tree. So for instance, what we mean by visiting is processing, like printing out the data, right? Based on the different types of ways that you can traverse the tree, it's known as either the breadth first traversal or the depth first traversal, okay? So for instance, it's kind of searching a graph, right? I mean, tree is only a special kind of graph. So in breadth first, we will visit all nodes at the same level before moving to the next level. So you have a tree here. So you will visit all nodes in this level before moving to the next level. That's a breadth first search algorithm, right? So for instance, in this figure, right, you go F and then DJ and then B, E, G, K, A, C, I, and H, right? That's the order in which you traverse. In breadth first, we first visit the children, right? Whereas for the depth first, right, you visit all the children first before moving to the sibling, right? The relative order could be different. Either you can visit the entire left subtree, or you can visit the entire right subtree, or you can start with a root, right? But the core idea of visiting a child is visiting a complete subtree is determined by the child. So for instance, you can go to a root, and then you can go to a left subtree, and then you can go to the right subtree. That's called a pre-order traversal, okay? Or you can start with the left subtree, come to the root, and then to the right subtree. That's called an in-order traversal. Or you can go to the left subtree and then right subtree and then to the root. So it would differ. For instance, let me see if I have an example here. So even here, right? So if it's going to be an in-order or a pre-order, so you first have this, you go and go to D, and go to B, and then go to A, and then go to the root, and then go to C, right? And then go to again E, and then F, and then you have this, you can access these nodes, okay? And so there are different, or you can start with these nodes and then go to the tree and then go to this left subnode of the tree, right? So these are two types of visiting, and according to that, you will see that it's you will have different types of according to different type of traversal, you will have a different way the nodes that you can access. Right, and another example of a tree data structure is a heap. This is a special type of a data structure, similarly like what we had queues and priority queues and queues and stack for a linked list. You can have a special type of a tree called a heap. The heap is simple. The parent node, the value in the parent node should be either greater than the child node. In that case, it's called a max heap. In some cases, if you have, or in the cases you have the parent node values less than the child node, it's called a min heap. Okay, so for instance, this is an example of a min heap, like 10, the value is lesser than 14 and 19, and 19 here it's less than 42 and 27, right? So this is an example of a minimum heap. Okay, and there are these are important ways of data structures, and in graph algorithms we will see one such algorithm today. Okay, it's important how it is implemented. The data structure behind it would determine the complexity of how good the algorithm is going to be. Okay, so graphs are non-linear. They are similar to trees, and they are non-hierarchical data structures. Okay, you have to compare this with trees that are non-hierarchical too. But graphs are non-linear and non-hierarchical, whereas trees are hierarchical, right? There are several applications of graphs, and almost everything, the systems, right? If you have a gene expression, and if you have, gene to gene signaling and things like that, I mean, it's all represented as a graph, right? So the social network, it's again a graph, right? So it's a simple collection of vertices and edges, okay? And if we apply the previous interpretation of a node, a graph is just nothing but a bunch of nodes, actually, right? And everything you can think about linked list is a graph at the end of the day, where you have a single, it's a tree in fact, with a linear structure, right? So it's not a binary tree, right? It's a tree, right? If there are nodes, n nodes in the tree will have n minus 1 edges, right? For one edge for each parent-child relationship. So all nodes should be reachable from the root, and there should be one possible path from the root to node. I mean, there are no such restrictions for a graph. These are the difference between a graph and a tree, right? A tree is a special type of graph, but a graph is a more generalized form of a tree, right? A tree is a special type of graph, and there are two types of graphs. You can have a directed graph, or you can have an undirected graph, right? So a special type of a graph is called as a weighted directed graph. So you have a weight here. So for each of it, you can think of it like this. You can think of these are cities, right? Let's go for one of the famous examples. Let's say that these are cities, and let's say that these are the cost that happens to go from one city to other, from New York to, somewhere in Philadelphia. It takes about 8 units of it could be anything, right? Fuel or something like that. So you can think of it a graph, right? I mean, this graph structure, you can think of the graph structure as a social media. You can model all these social networks and stuff like that based on graph. And this directed graph is one of the most finds most applicable in several problems. And these graphs are usually represented through what is known as an adjacency matrix. So you have a graph here, 1, 2, 3, 4, and you have a directed graph here, right? So what you do is you have these graphs on your on the rows. You have the vertices. You arrange the vertices on the columns too, and you put the weights on these. So the one-to-one, there is no self loop in here, so it's 0. A graph could have a self loop too. Okay, there could be a loop that's coming back to it. And so 1 to 2, right? 1 to 2, the cost is 1. And 1 to 3, the cost is 12. So you can represent the entire weighted directed graph as an adjacency matrix. This is called as an adjacency matrix. Okay. So one of the important problems that happens is what is known as a shortest path. You have a graph, you have a start position. Let's say you have cities, and there are some cost for breaching from one city to the other. It could be money, it could be anything. And you have to find the shortest. You are interested in finding the optimal path, right? From one start to the end, to the start to the end position. And that's given by one of the classic algorithm is called the Dijkstra's algorithm. Okay. So Dijkstra was one of the pioneers of algorithms. He was in UT Austin. He passed away like 5 years back, I think 5-6 years back when I was studying. But he's one of the pioneers of several algorithms. So let's watch this path planning. So you have A, right? You have a vertex A, and you have G, and you have to reach from A to G, and the costs associated on these. For A to C, it's 9, etc., etc. And you have to find the shortest path. To do that, what you do is you maintain, right, a list, maintain a graph here, right? And where you have the unvisited node, and you have the visited node here, and you have all these vertices in here, right? So at 0, initially when you start the program, right, you have all these are all unvisited, and you put infinity here just to make sure that it's the most expensive cost. Right now you really don't know what's the cost that's going to be, right? So that's why you put infinity, meaning that you really don't know what's the cost yet, which path is the best path. So that's why you assign infinity value, some large value. I mean, in real applications, you could apply, have some large value, right? And also you maintain this matrix. So what this matrix says is that this is the cost that you really don't know at 0 position, right? You really don't know what's going to be the cost. Now, what happens is at iteration 1, right, the first iteration, you find the minimum distance, what's the distance from a node to the next node that is available, right? So for instance, you start with A and you have to reach G, right? So from 0, you visit A, right? That's the first one, and these are all unvisited. And what happens is that A to A, you're already in A, so you don't really assign anything in here, right? Now A to B, right? What happens from A to B? The cost is 16, and 16 is less than infinity, right? So so it's fine. You're going to put as infinity 16 in here because the cost is less than what it's going to be here. Now you look at from A to C, the cost is 9, which is less than infinity. That's fine. You put 9 in here. Now what happens from A to D? There's no from A to D it's 35, right? So it's fine. So far the first is fine. The first iteration is going to be fine. Whatever the value, most of all the values are going to be less than infinity. So it's going to be 35 here. And what happens to A to E? Is there any node from A to E, edge from A to E? No, right? So there is no edge, so just put infinity in here. So we can't really go from A to E. Now, once this is done, the next is actually going from from A, one of the nodes that was visited from A. So C was visited from A. So you take C, right? Now C gets visited, right? So from A you come back to C. Now what happens at C? You compute the distance of going from C. You are in A. You came from A to C, right? So the length, and also you make a table here that says that from and to, right? From A to C, what's the cost? What's the length of it here? It's 9, right? Now you take this value 9, and then you compute what's the cost of going from C to A. It's fine because you already visited from A, so you don't really compute what's cost it's going to go for A. Now from C to B, from A, right, you are visiting C to B, so the cost is 16 plus 9, which is huge than 16, right? So that the value is going to be just 16 in here, right? And C to C, you're already in C that you don't traverse. Now C to D, right? C to D is 9 plus 15. It's 24, which is less than 35. So you have that 24 in here, right? That's fine so far. And then also compute what happens from C to E. There is no edge. Now C to F, right, 22 plus 9 is 31, which is less than infinity, so you have 31 here, right? And there is no edge between C to G, that's fine. You don't really have anything in here, so it's infinity. Now, next, the third iteration, right? So you have visited A, C, and now you're taking B, right? Now from B, you are already computing A, there is no, you are already gone from A, right? So you don't really compute what's going to be in A. So it's a very natural way of doing if you think about it. I mean, at every time, you are computing the best possible ways to go depending on optimizing the cost that you have done so far, right? From A, again you go from B and B to A, and you have to only compute from B to D now, right? The cost is 16 plus 12, which is 28, which is higher, so it will not visit D, right? So it will not visit D, and you have the same cost distance in here, right? So for the optimal distance, you see it's A, C. That's the optimal cost that's being done so far here. So you do this kind of a procedure. I'm not going to go over this in detail. And then you finally reach D, these matrix that will tell you what's the optimal cost in going from one to another, one node to the other. The cost would be C, A, C, F, and then G. So that's going to be the final cost of going in. I mean, so at every stage, you compute all the possible ways that you can go to that node, taking into consideration the previous nodes that you visited. Okay, so this is one of the very powerful algorithms, and the complexity of it is it's pretty good actually. Depending on, it's usually implemented as a minimum heap, and in that case, the complexity would be the order of vertices plus edges. Okay, so that's the demo of who wants to be a millionaire here? Everybody? Everyone? Okay, it's pretty easy actually. The problem is very simple to state. Have you heard of this problem called QMB problem? Completeness? Okay. All right. So far we saw sorting algorithms, right? So what was the complexity of selection sort? Yeah, order n squared, right? And and you can, there are several other sorting mechanisms, and some of them would be linear sorted, order of n, and things like that. Okay, so these are all polynomials, right? N squared are all called polynomials. So the set of problems that you can solve in polynomial time, okay, it's called the class P. Okay, set of all problems. Sorting is a problem that you can solve in polynomial time. So it's simple, right? And there are some problems that you can, like for instance, have you heard of traveling salesman problem? Right? Is it polynomial? Could be.
It's like sorting problem, and you shouldn't reach. I mean, they have the list. Yeah, they have the list, so they have to go through different places,
Mm-hmm.
and they have timing
Right.
as well.
You have to optimize the time or the cost in reaching. You have to reach every city, right? With optimized cost, right? So most of the graph theoretical problems are notoriously bad, that they are, you don't really know if it is polynomial or not. Okay, so those problems, some of them are exponential in time. Okay, so you can compute that. If you, the brute force algorithm, the basic algorithm, you can go to every vertex every time, right? That's a very basic algorithm. If you do that, that's exponential in time, right? So but then if you give if you give a path, you can verify whether it takes polynomial time or not. You can verify the solution in polynomial time. Okay, so those problems are called NP. Okay, so what that means is, I'll give you a path. You have a traveling cities, right? N number of cities, and there is a cost associated with it. You have to travel each city with minimizing the cost. And I'm telling you, okay, this is the way. These are the path that the person should travel. You can immediately verify, right? Write a program to verify it. and that can be done really fast, right? So these problems you can verify in computable time, in polynomial time, but you may not find the general solution of that problem, right? I'm asking you to give me the general path. I can give you any set of vertices and you have to give me this any set of paths, right? That you have to give me the set of path that optimizes, minimizes the time, right? You can't really do it in polynomial time. You don't know whether you can do it in polynomial time. But if I tell you, see if it is the solution, this is a solution, you can verify it in polynomial time, okay? This type of problem is called NP problem, okay? And there is another class of problem called NP hard problems, okay, which are as hard as the problems in NP. So, for instance, if I have a problem in NP, you can reduce that problem in every problem in NP. You can reduce every problem to that problem in NP. What does it mean by reduction, right? So, let's say a simple example. Suppose you know that, suppose you know how to add or subtract and take squares and divide by 2. These are the operations that you know, okay? So with this knowledge, you don't know how to multiply. With this knowledge, we can find the multiplication, right? By a plus b whole squared using this formula, right? You really don't know how to multiply, but you can use the knowledge for squares to multiply. In that case, the problem of multiplication gets reduced by the problem of computing the squares and adding and subtracting. Okay, so these are two problems. I'm giving you two numbers, multiply two numbers. That's my first problem. The second problem is I'm giving you two numbers, you can add, subtract, or squares or divide by 2. Okay, now these two problems, one can be reduced to the other because of this formula. Because you know that, then I can always do this multiplication. So if you know the solution of one problem, you can reduce to another problem, solution of another problem. Okay, so the set of all possible problems where one can be reduced to the other, it's called NP hard. Those are NP problems, but they can be reduced. Let me show you an example better, okay? So problems in NP hard do not have to be the elements of NP, but they may not even decidable. Like for instance, traveling salesman, right? This is a very hard problem because we really don't know the solution yet in a polynomial time, right? But you can verify. But the NP hard problems or one can be reduced to the other. So for instance, the class of all problems, right? This is let's say that this is a polynomial problem. This is a possible Venn diagram, okay? This is called, there is another class called NP complete. The class of all problems that belongs to NP as well as NP hard, okay? So NP hard consists of all problems where you can reduce, if you reduce one problem, you can reduce all problems. You can solve, if you solve one problem in polynomial time, you can solve all problems in polynomial time. Okay, so this is, let's say that this is a polynomial time problems. The complexity is polynomial. This is NP problems. Okay, we really don't know whether they can be solvable in polynomial time, but they can be verified in polynomial time. Okay, and NP hard is a class of problems where if you reduce one problem, you will reduce all problems in polynomial time. Okay, so this is a possible Venn diagram because you really don't know if NP can be polynomially reduced. If you reduce one problem in polynomial, you can reduce all problems in polynomial. Okay, and so completely P will be equal to NP. It will collapse. It will completely collapse. The class of NP problems will come, NP complete problems will be collapsed to polynomial time. Okay, so even if you solve one NP complete problem, there are so many problems out there which are NP complete. So if you solve one problem, you can solve all problems in NP complete problems because one can be reduced to the another. So let's say that this, for example, this, right? Let's say that this is an NP complete. You know that this problem is NP, NP, right? This you know that you have squares, but you immediately solve this problem because you know this formula, Okay, so this is a class of, so immediately everything will collapse and it will give you this Venn diagram. That's why I said this is a possible Venn diagram. This is not a real Venn diagram. Okay, so this is one of the, otherwise the Venn diagram doesn't change. It's going to be like this. Okay, so this is one of the Clay Institute's million dollar problem. It's one of the, you know, toughest problem in computer science, and this have real world ramifications. Think about it. Some of these problems, like the credit card security and things like that, you make, how are these security systems are made? Some of these security systems are made so that people can't easily break the codes. It takes exponential time to break the code, right? Nobody has, it takes like millions of years to find out the password, for instance. That is how the codes are designed. Okay, but these are NP complete. Even let's say that if the solution, if you can solve one problem, that's it. I mean, all the security is breached. It has a very wide real world applications, and I mean, if you saw, I mean, that's why it's one of the hottest problems. So people, we really don't know whether P equals to NP, and if you want to take it up as a challenge, you can work through it. You know, I mean, there have been like 3 months back, there was an art, not 3 months, like just a month back, there was a claim saying that one of them has solved P equal to, and became a big news and stuff like that. But they found out a flaw in the proof. I mean, this happens all the time. I mean, people submit claim that they have a proof, but nobody is able to ever prove that P equals. I mean, it is generally accepted that P is not equal to NP. I mean, it's generally, I mean, you know, if you prove that P equal to NP, like, you know, if you solve an NP complete problem, you would be like, you know, immediately world famous. But so far, it's people generally think P is not equal to NP. That's the consensus among the scientific community, at least. So yeah, there are very good resources for algorithms. I mean, it's one of the fascinating subjects and a very important subjects, given that, you know, we are all, the computation is going to be really, you know, going towards the quantum. It doesn't matter whether it's a quantum computing or fundamentally it's run by algorithms. It's, you know, whatever that's being done, all these things, right? It has, the basis of it is algorithms. It's a fabulous area, actually, you know, a very nice area. If you develop some good algorithms which can be, you know, used. I mean, most of the biological problems are hard. It's our graph theoretical problems, right? I mean, cell signaling and things like that. These are systems biology problems. It's network biology at the end of the day. One can be reduced. Like, for instance, you can think of a reduction like this: a gene expression, right? It's similar to traveling salesman problem. All you need to do is, instead of cities, you just have genes in here. I mean, it's a reduction, direct one-to-one correspondence in here, right? So uh, it's a classic area, and good algorithms are needed. Like BLAST, for instance, right? It's, everybody knows used BLAST here, right? It's a string matching algorithm at the end of the day, right? Smith-Waterman algorithms for genome mapping. So this is what the heart of computer science. It's what that runs, you know, computational biology. I think today I don't think we have anything for the presentation, but I think David has assigned you some things to present on these algorithms, right? I think I made three important things. One on heap sort, the other is on dynamic programming, and the other is on string matching. If you have get a chance, this is a very good book for algorithms. It's a gospel, actually, Introduction to Algorithms by Corman Rivest. This is what I studied when I wasn't doing computer science, and it's one of the, it's a huge book. It's a very nice book. It has all these things, so it's worth, if you're interested in studying this further, I think it might be worth you know. But then there are lots of resources out there. If you want to self-learn, there are lots of things out there. So it's just a recommended book for learning some of these things. Any questions? Nope.
So what was the presentation?
Oh, he would, I think he would assign something for presenting in these, some of these topics, like heaps of dynamic programming and string matching.
Okay.
Yeah, he would
So
come.
he'll essentially assign us something, tell us more about that later.
What's that?
He's going to tell us more about that later.
Yeah, right. Yeah, and especially to do good data science, these are all fundamental things that I should know. There are exciting books to understand from a more for NP completeness. I think there are lots of resources out there. These are problems in logic. Some of the logical problems are NP complete. I mean, these are like 3 SAT. There are some basic problems that are NP complete. But yeah, with this, I'll stop for today and I'll let you go. Uh,
No, so I couldn't get it to